Got it. इसको प्रेस करना, स्टार्ट करना. Good afternoon, viewers. Myself, Surendra Kumar from the Department of Electronics and Communication. I welcome to all my viewers in this online lecture. My topic of today's lecture is transistor configurations. And this is very, very important as electronics engineer points of view, that to know about the all these three transistor configurations before using the transistor in our circuits. So on the basis of configuration, we will decide which configuration will be best suited to our circuit and our applications, so that we can take the distortionless output. So in this regard, today's lecture, we will discuss all transistor configurations, their properties, characteristics, and some important current equations and some important parameters like input impedance, output impedance, current amplification factor, voltage amplification, and phase difference between input and output signals if we use these three configurations. So let's start from the first slide. Okay. So this is the first slide. Here, this is the basic things about the transistor configuration. Transistor configuration is the way of transistor connection in the circuit. So it's all about the connections of transistor. How many different way a transistor can be connected in the circuit. So each configuration has particular characteristics that make it for specific applications. As I have discussed just before, in each and every configuration has its different kind of value of parameters. The following parameters that we are going to discuss with each type of configuration of transistor. These are the important parameters like current gain, voltage gain, input impedance, and output impedance. On these important parameters, on the basis of these important parameters, we will decide which particular configuration of transistor best suitable for our application, so that we can find out the maximum efficiency of our circuit in the application. Understanding these different configuration of transistor will help you in better implementation of your application. So if we have the proper knowledge of every configuration, the parameters of configurations, so we can make best use of our transistor in the circuit or different kind of applications. So let's move towards first configuration. Types of configuration. Let's talk these three different type of configuration. First one is common base configuration. Second one, common emitter configuration. And third one is common collector configuration. As the term common is used in these three configuration, which denote the element that is common to both input as well as output circuit or output side. As we know, a transistor is a three-terminal device. So on the basis of three terminals, we make a connection in three different modes. So with a particular terminal, we goes to make a circuit. So in this first configuration, the circuit is shown over here, in which the base terminal of transistor is common for both sides, input as well as output. So this is the circuit for common base configuration of transistor. And in this second one, ammeter terminal is common for both sides, as well as input as well as output sides. In third one, it's very easy to identify which type of configuration is this. In this particular type of configuration, our collector is common for both the sides, input as well as output. So some more important point we can also discuss in this first configuration. You can see that ammeter is input, collector is output, and in the second one, base is input, and third one is base is input. So we can see a base is always will be the input. It cannot be considered as a output. Ammeter can be considered as input as well as output. You can see in this first circuit diagram, common base configuration, ammeter is input terminal, and in this third one, common collector configuration, ammeter is output terminal. So we can say ammeter can be considered as a input and as the output. Collector, what about collector terminals? You can see in this first configuration, collector is the output terminal, and in the second, collector is also output terminal, output, and here in this third common collector configuration, ammeter is output. So about the collector, we have a particular data that it can be used only as a output. It cannot be used as input. So I want to repeat this thing once again, but it is very, very important and to know about the terminals, which terminal can be used as a input and can be used as output. So I repeat, ammeter can be used as input as well as output. Base, it can be only used as input in the circuit, and collector can be used as output. So only ammeter is the terminal that can be used for input as well as output. Next, this is the first configuration, common base configuration of transistor. Here, the same circuit we have made with the input signal, which is the AC, with the biasing supply VBB and VCB. In this circuit, first let's know about the biasing technique, what kind of biasing technique we use with the transistor while we are using in our circuit. So always the ammeter base junction of transistor should be connected in forward biased, and collector base junction should be connected in reverse biased. If we bias the transistor as per the technique just before that I have discussed just before, the transistor can be used in active region. So the best use of a transistor or transistor amplifier, its active region is very important. So to use the active region, this type of biasing should be there. So you can see in this circuit diagram, common base configuration, NPN transistor I have used, here, and the base terminal is connected to the positive terminal of the battery, and ammeter is connected to the negative terminal of the battery. Here ammeter is made of N type. So when N region of the transistor is connected to negative, it will be in forward biased. So here we have to only consider the biasing supplies for DC analysis. So we ignore this signal, and you need to consider this short circuit. Only DC biasing is there, input side and output side. VCB, this connection of the battery, VCB, its positive terminal is connected to the collector, which is made of N type of semiconductor. So if N type of semiconductor is connected to positive terminal of the battery, so it makes it in reverse biased. So both the important biasing technique we have used, so that this transistor will work or will operate in active region. So let's do some important analysis of this common base configuration. What kind of properties, what kind of current relations we have. So as you see, the direction of currents related to each terminals. Here we have ammeter current IE with base current IB, and with this collector IC current is there. So these IC and IB, these two currents are incoming, and I is the outgoing current. So by using KCL, we can relate all these three currents. So by using KCL, total outgoing current equal to incoming current. So IE is equal to IB plus IC. So IC collector current is the combination of two important currents, I majority plus I minority. Here I majority indicates the current which constitutes by the majority charge carriers, which are the electrons in NPN transistor, and I minority, this is the current which is because of minority charge carrier, and holes are the minority charge carriers in this NPN type of transistor. So the major current that is I majority, that is equal to alpha IE plus ICBO, where alpha is the current amplification factor, and ICBO is the reverse saturation current from collector to base when third terminal is open, as shown in the circuit. So to understand this phenomena, how we can calculate ICBO, and what is the importance, and what is the condition for which it flows. So if our IE input side IE is 0, then there will be only a VCB output battery is active in the circuit. So if VBB is equal to 0, or putting equal to 0 potential, so in that particular case VB will be 0, so ammeter current will be 0. So for the ammeter current, there will be only leakage current in the transistor, and the direction of that leakage current will be from collector to base terminal. So this is the direction of ICBO, which is shown in this circuit diagram, and here suffix CBO represents the direction of current collector to base when third terminal ammeter is open. Here alpha is equal to IC over IE. This is the ratio of collector current over IE, and alpha is always less than or equal to 1, because the current IC and IE both are approximately equal to each other, because the base current in this first equation is the very small current, because the base of transistor valley is small in region, so it constitutes very small current. So the range of base current is in microampere, and the ammeter and collector current flows in the range of milliampere. So it's very small current in the transistor. So the difference between these two current, collector current and ammeter current, is very small. So always collector current is slightly less than ammeter current. So we can say the amplification factor of transistor in common base configuration is equal to 1 or less than 1. So it was the current relationship between common base configuration. Now let's discuss about some important VI characteristics of common base configuration. In this first characteristics, we see the input characteristics, which is drawn between input voltage and input current. And in common base, VB is my input current, sorry, input voltage, and I is the input current. It looks like diode characteristics. Already we know about the diode characteristics is just like the voltage source. So in this VI characteristics, you can see there is a sharp change in current as compared to voltage variation. So it belongs to the property of voltage source. A voltage source always provides the constant voltage, whether there will be a change, there may be a change in current. And if a voltage source, if you are going to represent, say, voltage source with its equivalent internal resistance, always it refers to very small value. So Rin, input dynamic resistance of transistor in common base configuration, it is the ratio of delta VB over delta IE. This is the change of VB, and this is the change in current for a constant value of VCB. Here you can see the change in VB is very small and the change in current is very large. So the value of this mathematical function will be very small, and the range of this Rin, or you can say dynamic input resistance, is just around 50 ohm. Now this is the output characteristics of common base configuration. It is plotted between output voltage, which is VCB, and output current, IC. Here, when the IE is 0, the collector current is not 0. Already this point we have discussed in previous slides, where we are saying that if ammeter current is 0, there will be only leakage current will flow in the circuit, and the direction of that leakage current is collector to base and is denoted by ICBO. And here, this is the graph for which we can say the leakage current is flowing and ammeter current is 0 milliampere. The curve of the active regions is almost flat. You can see after a particular value of the VI characteristics, after this point, the level of current is almost constant and it is independent of VCB. There is no any effect of this change in VCB. Third point, collector current does not depend on the VCB. Already we have discussed this point. Now you can see the graph starts from negative side, because if the voltage VCB is 0, so the only input side battery VEB is working. So because of that, the transistor will be in saturation mode. So because of that, there is a negative polarity of VCB will be formed, and your graph will start from the negative side of the VCB. This is the active region, for which we have almost constant current in this area, and in the saturation region, this is our linear region, where we have the straight line of this curve. And the dependency of this current IC, already we have discussed IC is equal to alpha IE. So it depends on the IE. And most important point that also we have discussed in previous slide, IE is always slightly greater than IC. So in this graph, you can see this solid red line showing the collector current, while the dotted line represents the ammeter current. So red line always will be below this dotted line. Now calculate how can we determine or calculate the output impedance of common base configuration. As we see the characteristics of a transistor, here the current is constant. So this property belongs to the current source. A current source always provides the constant current, whether there is a change in, there may be a change in voltage. So every current source, if we replace with its internal resistance, it's very high internal resistance if we replace with its internal resistance. So the value of output resistance will be very high. The mathematical expression for this already we have discussed. RO is very large, and the value of this RO, dynamic resistance of base configuration, is around 1 mega ohm. It's quite large value of resistance. So this is the common base configuration, and we have discussed input impedance with the help of input VI characteristics, and output impedance with the help of output characteristics. Now this is the common ammeter configuration of transistor. In this common ammeter configuration, ammeter is common, and here we have apply a input signal. VBB and VCC is the biasing supply. Now we have to rewrite this collector current equation in terms of the input current. Here collector current is the output, while base current is my input current. So it can be represented in terms of input current, which is base. So we don't want ammeter current in this expression, so we can replace this ammeter current in terms of IC plus IB. So IC 1 minus alpha over here, and that will be equal to alpha IB plus ICBO. Here finally this expression can be written as alpha over 1 minus alpha IB plus 1 upon 1 minus alpha ICBO. And this alpha 1 upon minus alpha IB plus ICO, there is a new parameters we have introduced, ICO. This term represents the leakage current in common ammeter configurations, while ICBO was the leakage current in common base configuration. Beta IB plus ICO is the final expression of the current equations, collector current equation, you can say. Beta is current amplification factor in C mode, already we have discussed. Beta, the value of beta, current amplification factor, the mathematical expression is alpha over 1 minus alpha. Beta is very high because the value of alpha is always less than 1. So the range, you can say it will be around 100, it's quite large. So reverse saturation current ICO from collector to emitter when third terminal base is open. So it was the current relationship between different terminals, IB, IE, IC. So it is a little bit different, in which we have expressed our collector current in terms of base current and leakage current ICO. This is the input and output characteristics of common emitter configuration. Input characteristics is plotted between VB and IB. Here you can see again, this is looks like the diode characteristics, but the slope is totally changed. So in this case, if slope is a little bit changed as compared to common base configuration, so in this particular case, our input resistance that can be represented by delta VB over delta IB, it is comparatively large, and the range is around 1 kilo ohm, you can say. The output characteristics, again, it is look like a current source, in which you can say the current is constant and it is independent of voltage VC. There is no effect of change of voltage VC over here. And the dependency of this collector current here in this particular graph on base current IB. These are the important points or properties of common emitter configuration. When the IB is 0, the collector current is ICO, the slope of the curve is quite more than CB configuration. The curve of the active region is almost flat. Collector current does not depend on VCB. All these three important points already we have discussed. So RO, output dynamic resistance of common emitter configuration. The mathematical expressions can be written as delta VC over IC for a constant value of IE. For a particular graph, we need to put IE as a constant value. Here RO is very large because the slope in case of common emitter configuration is greater than the common base configuration. So because of that slope, the value of resistance is larger. So it is around 50 kilo ohm. Common collector configuration. In common collector configuration, here the emitter current is our output current, as we have discussed in the starting. So the level of this current IE is just equal to the collector current. So in this first two configuration of transistor, IC is the collector current is the output current, and in the second one is also collector current is output current. Here emitter current is output. So this is the only change in common collector mode of configuration. And the level of emitter current is almost equal to the collector current. So the characteristics of in terms of output characteristics, if we talk, the almost equal to emitter common emitter mode. So the output characteristics of common collector and common emitter configuration both are almost same. Current amplification factor is almost same. The change is the voltage gain. The voltage gain in common collector configuration is equal to unity. So there is no any voltage gain. So it cannot be used as a voltage amplifier. Now, if we do the comparison, all these three important configuration of transistor. So these are the points on the basis we can make a valuable difference between these three configuration. Parameters, voltage gain. In case of common base configuration, we have important thing that the current gain is unity. Otherwise, we have a high voltage gain and moderate power gain over here. In common ammeter configuration, voltage gain is also high, current gain is also high, and power gain is also high. So this common ammeter configuration is best suited for the amplifier circuit. So it can be used as an amplifier. Common collector configuration, the voltage gain is less than unity and current gain is high. Already we have discussed the collector current gain. Current gain in common collector configuration is just equal to common emitter, and the power gain is moderate. Phase inversion, there is no any phase difference between input and output signal if we talk about the common base configuration. In common emitter configuration, there is a 180-degree phase shift between input and output signal. In common collector, there is no phase shift. So in terms of phase shift, there is only one configuration we have for which there is a 180-degree phase shifting is available. Input impedance, low. It is very low value for common base. It's moderate 1 kilo ohm and it's very high 3 kilo ohm in case of common collector configuration. Output impedance, it is high 1 mega ohm, it's moderate 50 kilo ohm, and it is around 300 ohm for common collector configuration. If we talk leakage current, it's very small, 5 microampere, and it's very large in case of common emitter and same in C configuration. So it was the comparative statement about the three configuration of transistor: common base configuration, common emitter configuration. So I hope it will help you to choose better transistor connection which provides you the best output for your circuit. So that's all from my side, and if you have any query, you can put your queries in the chat box.